Yeah, the world's going to get really complicated. I mean, it already was, but you guys are Gen Zers, right? Are you Gen Z people?
Supposedly. Yeah. But yeah, according to whatever definition.
Demographics. Yeah, Gen Z is going to have to rescue the world. I hate to break it to you, but we've all been sort of B-plus generations until now. You guys are going to have to be A-plus. Not to put on the pressure or anything, but...
Yeah, no pressure at all.
Which problem would you focus on today if you were a Gen Zer?
Oh, God. You just... there's a lot. I mean, I know a lot of people worried about the environment. Like, how do you manage the world, you know? You guys worried about that, right?
Yes.
Yeah. Yeah, that's a big one. Yeah, just keeping democracy working and keeping the country going, and none of these things are, unsolvable, but, and I think you can do it. And I'm not dead yet, so I'm going to be helping, but, yeah, there's a lot to do. Can we talk about something more specific? Because I'm not good at grandiose lectures on...
Yeah,
something specific you wanted to discuss?
Yes. Oh, wait, also, before anything happens, like, I'm just, like, shadowing, like, trying to learn how people make podcasts, so, like, you don't have to worry about... If I'm standing in your way, I can also move,
Well, it's fine. It's okay with me.
Okay.
And she's curious.
Yeah, I'm so curious.
I mean, ask something.
We looked into, like, everything that you were doing, or at least I was looking at it, and I thought, like, your experience, like, working at Enterprise Works was really cool, like, with your startup. Because I was, like, when you did talk about just, like, balancing everything, I thought that was interesting, because you're a professor, you do research, like, you have your own startup.
Yeah.
Like, how is it managing all of that, and how do you, like, prioritize, like, what is important to you?
Good, that's a great question. Okay, that's something more specific. So you're talking about time management, or why do all these things?
First, I think why do all these things?
Maybe we should roll the camera. Yeah, I think the thing is, when they hire you as a professor at a place like this, you sort of have, there's no intrinsic limit on what you can do, right? You sort of have this vast expanse of space you can expand into, and the only thing that stops you is your own energy and limitations and imagination. And, you know, it's tempting to just try to do all of it. And because you only live once, right? So I think, yeah, so I've really tried to take the job seriously and do it the way it should be done. You know, you get tenure, and tenure is a controversial thing these days. Some people think we shouldn't have it at all. But what it's supposed to be for is allow you to take risks, you know, that's... So, yeah, I mean, I started a company because this is just the warm-up part, right? Or should we start the podcast part? Because this is all stuff. Yeah, so the question is, why did I do that, or how do I manage it?
First, why did you do it, and then how do you manage it? Like, do you chase after things that excite you usually, or do they come to you and then you go after them?
Yeah, I get wrapped up in an idea and I can't put it down, and then I go after it. These are good questions. Yeah, so that's kind of how it starts. I think also, so I'm an academic, but most people in my family, if you go back in history, were entrepreneurs. The only one who wasn't was my grandmother, who was an accounting professor at a city college in Chicago, Orville Wright College. She taught cost accounting there for a long time. Everybody else in the family is an entrepreneur, so you know, you go to family events and they kind of stare at you like, you know, you're living off the government. Good job, you know. They sort of. So I always kind of carried this sort of guilt along, and I did my PhD I actually got my degree here, but I did all my research at Bell Labs. Do you guys know about Bell Labs?
Yeah.
Of course. Yeah.
Because it doesn't exist anymore.
Yes.
I mean, this is for me, by the way.
Yes,
Yeah,
it is.
Yeah. Yeah, it doesn't exist. I mean, it's formally still there, but almost everybody's gone. And my dream in life was to go to Bell and do some combination of basic research and industrial R&D and tech transfer, and I was going to live the rest of my life there. I didn't ever want to leave, and it just disappeared, you know. And there's a whole story why that happened that I could explain if you want to know. Yeah, I sort of spent the next 10 years drifting around trying to figure out how to recreate that Bell Labs experience somewhere. And so actually, you know, when I got my PhD, they wanted to hire me, but they were firing people and not hiring anyone. And I had no idea what to do, so I moved to Europe with my girlfriend. So we just moved. Actually, we were married at that point, still are. But yeah, we just moved to Europe, had a baby, had no plan, just moved to the Netherlands, to this little town in the north called Groningen. And then, yeah, and I wasn't sure what to do, got involved in some really innovative science, and then came back to the U.S. and I thought, okay, I'll go work for a national lab. You know, there are these government-run laboratories like Brookhaven National Laboratory, Argonne, SLAC. And I thought, okay, maybe that's sort of a sweet spot, sort of in between industry and academia. So I went to Brookhaven, and I really liked it, but it was really very governmental. It wasn't a place to do really risky, bold, innovative research. It was in some ways sort of the opposite of that. So that was a little disappointing. And then I wasn't sure what to do, and then they recruited me back here. And I thought, okay, at a university, maybe I can then you sort of have a license to do anything you want. And then, so I came here, got tenure, and then I started a company. And it was kind of an attempt to rebuild this Bell Labs atmosphere of like basic science, industrially relevant, world-changing science, and then the stuff in between. And it's not perfect, but I'm working on it, still trying. Yeah. Anything else you want to know?
Could you actually explain a little bit more about Bell Labs and where that originated from?
Bell was amazing. Well, you know what it's in Murray Hill, New Jersey, and at its peak, there were thousands of people working there. And the building, I don't know if you've ever seen it. It's really a parallelepiped. It's a rectangle, right? Big thing, and it's like a mile long. You know, it's got this beautiful entrance with all these displays and history of Bell Labs, discovery of microwave background, CMB background, and inventing Linux or Unix and all that stuff. Anyway, you go in, and then when you get to the scientific part, you stand at a hall, and it's a mile. It's just a straight line. It's like 5 floors. And there's these parallel hallways, and just on either side is labs. And it was amazing. I mean, just the amount of stuff going on and just the level was incredible. And so many things happened at Bell Labs. I mean, they discovered the fractional quantum Hall effect. They invented, I think I already said, Unix. They invented the transistor, right? Integrated circuits. They invented molecular beam epitaxy. Like almost, it's like a significant fraction of all innovation that happened in North America in the 20th century was at that one building. And yeah, it was my dream to go there and never leave. And it was a really rough and tumble environment. I mean, people shouted at each other and insulted each other. In 2020, what year is it, 2023? I can look back on it now and recognize it was toxic masculinity, was what we call that now. So a little revisionist history going on. And and but it was exciting. And the flip side of that was you had to be on top of things all the time because you could not get away with BSing your way through anything because someone would hold your feet to the fire and hold you. So you had to be at the top of your game. And I don't know, I always found that, I liked that. But yeah, as time went on, it came to be clear that it was a sort of a mythical, it never should have existed. Do you know why Bell Labs existed?
Why?
So in the, I'm probably going to say, it wrong, but AT&T was the parent company of Bell Labs. It was their R&D lab. AT&T was a regulated monopoly. So during the Guild era, laws were passed, and one was the Sherman Antitrust Act?
I think that was the one that break it up.
Well, they broke up the baby bells in the 80s, but in the 20s, I think it was. I'm going to embarrass myself if I get the dates wrong, but there were laws passed to regulate monopolies.
Right.
Standard Oil, U.S. Steel, these things all became regulated by the government because monopolies were basically taking over the country in the late 19th century. And then what happened was somewhere in this legislation there was a rule that said that regulated monopolies had to put 1% of their research into R&D. And AT&T became a regulated monopoly, and eventually it ran all the phone networks in the all of U.S. and Canada. And its revenue was so enormous, this 1% or whatever it was, I don't remember the exact number, maybe it was 0.1. In the 1970s was $1 billion a year. And they just took that money and they dumped it into this lab because they had to be in compliance with this, this law. So I don't know. I think what I was enamored with as a young person and saw as this extraordinary place and extraordinary people only existed to satisfy some law that was written in the 20s. And then in the 80s, they broke up Bell Labs into the baby bells, Ameritech, 9X, Pactel, all these things. And then it wasn't a regulated monopoly anymore. So they didn't have to put anything into R&D. And in 10 years, it was gone. And looking back, I'm glad I didn't end up there because I might have ended up a toxic masculine person along with the rest of them, and that would have been awful. So, I don't know. Is this what you guys wanted to hear about? Yeah, sometimes you got to be careful what you wish for. You might get it. I think coming here has been much better for me. I've had to be a better person. What was the question again? No, I forget.
What is Bell Laboratories? But I feel bad for asking questions.
You're doing a great job.
Just take your chair and
come here.
Over here.
Come here.
I'm so curious because okay.
Yeah, I'll check.
Here. It's a friend that wanted to join.
I met Aryaman like a week ago actually, and then he told me about this great podcast, and I was like, I need to know more.
Yeah.
But I was just really curious because you said that Bell Laboratories is what inspired you to create your own startup.
Yeah.
And so, like, what do you think you took?
That and the guilt trip of my family. Yeah.
Yeah, because you came
Right.
from a family of startups
Yeah.
or like
But entrepreneurs.
Yeah. So how do you think like your experience with Bell Laboratories and like your experience growing up in a family of entrepreneurs like affected how your startup is today?
Beyond just founding, well, my mother helped me start it. I mean, my mom's a CPA who ran her own printing company for a decade. So she, it was actually really easy for me to start it because I sort of, so you know about Enterprise Works. It's down in the research park. Mm-hmm. It's a great place. It's an incubator. If you have an idea for a company, you just apply to it. And if they like it, they give you subsidized rent, and there's accountants and lawyers and help you get incorporated and so on. I didn't need that stuff. I just called my mother, and And so it was really easy for me. So I think, how did it help? It just made it really easy. Yeah, I mean, what can I say? I'm from a privileged background, and I used it. I tried to use it for good. But I think this question specifically was, how did Bell Labs influence it? It ended up being, so the company's called Inprentus. They make what are called diffraction gratings, which are optics. It's like I don't need to get into gratings, but it's a flat surface with a bunch of lines scratched in it periodically, and they're spaced by a few hundred nanometers, so it's a nanotechnology company. So I think the sort of ambiance of a nanotechnology company that's manufacturing, that was sort of Bell Labs inspired. That's probably about the limit of it. I think U of I inspired it a lot more. I mean, I think the way the company ran, we really focus on we try to use the company as a way to hire young people, disadvantaged people, everybody we can find, and help move them to the next part of their careers. So we try to find a way to make the company sort of symbiotic with moving young people into the system. My favorite example is there was this PhD student in physics, and I won't specify the person's name, but they did their PhD in string theory, which is a very esoteric, very advanced branch of mathematics that's completely useless for anything. Actually, it's not true. There's some interesting applications in strange metals, which we could talk about. But and this guy was really good at mathematics and had absolutely no idea what to do himself. Didn't know where to find a job. Didn't know how to find a job. It's amazing what you cannot learn in the process of becoming a brilliant mathematician. And he graduated and just had no idea what to do. So we hired him at the company, and we said, do you know how to solve PDEs, partial differential equations? And he's like, yeah. We said, do you know how to do Python? He's like, yeah. We're like, okay, here's an algorithm. Here's some old papers from the 60s on calculating efficiency of diffraction gratings using recursive multiple scattering, which is a way of solving PDEs on the computer. Do it in Python. And he wrote a simulator for us. It was his first ever solving, a PDE on a computer, but he's like, I know how to code up PDEs. It's easy. And was really successful. And he ended up not staying with us. He went and worked for a quantum computing startup in California. And he's been pretty successful. He's, got coding up PDEs to solve equations of motion of superconducting circuits and stuff. So I was really proud of that because it took a person who was in a predicament, we got something useful out of them and helped them move on, right? So I think that's been, so the company's been sort of Bell Labs and U of I and inspired to be something useful.
How would you say it is like working with like the younger generation of kids as opposed to maybe someone like who is like the same generation as you?
Gen Z specifically, or any generation?
Because you're working with Gen, or like communicating across a bunch of different like groups is always difficult because you yourself don't understand it. Like, how do you?
Well, I haven't learned all my internet stuff
like
yet.
The slang.
I mean, I know TLDR and I know WTF and all those things, but I have two daughters that are Gen Zers, so I rely on them a lot for information. And they both went to U of I, so that's made it a lot easier for me. But yeah, I'm a Gen Z evangelist. I think you guys are going to be the heroes of the future. I really do. Do you want to get into that? What was the question again?
How do you communicate across like different age groups? But then on top of that, have you noticed like Gen Zers like ideas be different than people your age? Like, how do you think we think differently than like, people?
They're
like,
much more, okay, my generation, I'm a Gen Xer.
Okay.
So we're sort of a population dip in between the baby boomers and the millennials. And my generation had no idea what was happening in the world when we were in college and didn't care. We didn't know who was our congressman. We knew who was president. That was probably it. We were just focused on our own careers and our lives. Nobody knew much about international. There were a few people who were kind of into that thing or majoring in political science, but typical person just studying, I don't know, engineering or something. They didn't pay attention. They were just worried about getting a job and getting married and having a life, starting their lives. People now really know what's going on in the world. Do you guys know what's going on in the world? You probably do, right?
A little tiny bit of it.
I mean,
To an extent,
You're
right?
sort of forced to because you know we have news and just sort of
Yeah.
propaganda machine. Is
Yeah,
24/7.
maybe you just know the propaganda. I
Yeah.
mean, you know the war in Ukraine.
Yeah.
Okay, so yeah, Gen Z, I don't know, so for better or worse, maybe it's just circumstances, but Gen Z is just a lot more clued into what's going on in the world. That's my perception. And yeah, they seem to have more of a sense of responsibility for things. They seem to be a lot more conscientious about, yeah, just the future, environment, equality, you know, treating different people fairly. They just seem to care more about this kind of stuff. But you guys do you disagree with me? Or?
I would say so, but I mean, I think there are both sides to everything. Like, I think most of the people that you might have met would have been of that
Yeah.
spirit and nature.
That
But I
might be
feel
just
like
the ones
there
that
are
give
also
it-
a lot of complacent Gen Zers on this at the same time.
Yeah, could be they just don't come to talk to me.
Right.
Yeah. Yeah, could be. So I guess I can only speak of the ones that I know.
The physics people probably.
Yeah, maybe. Yeah, it's true. I meet a lot of physicists.
You know, when you talk about Bell Labs, you talk about basic science in applied research. You could probably bring up Vannevar Bush when he wrote the Frontiers of Science
Yeah.
in 1940s. The government just give money to basic scientists so they
Yeah.
can basic research. They can do whatever the hell they want. That's one side. Bell Labs, which is sort of this weird thing where you have all scientists, anyone who was smart and wanted to work hard, they would go there,
Yeah,
and that inspired you.
it did.
That's not a thing anymore. Every big corporation have tried to do that. There are books about it called The Idea Factory.
Yep.
We don't really know why it worked and how it worked, so it's just sort of a mystery. But when you look at, let's say, a startup or academia, which you have sort of both, there are different models to advance and make progress in different fields.
Yeah.
Both have big pros and big cons
Yeah.
as a way to improve innovation. You've done both.
I've
They started
done
for
both.
11 years,
Yeah.
since 2012. If you had to, maybe pick one over the other, or like for what sort of science is a startup better and academia better?
Yeah. Okay. The new system is much better.
Of academia?
Okay, so I think you were asking about the old model for doing industrial R&D, Bell
Sure.
Labs, IBM, TJ Watson, Xerox, PARC, versus the modern one, which is small startups that are spin-offs from mostly universities. The new system is way better, hands down. I don't think I'd go back to the old one at all. And I'll tell you why. The old system was not, I think when science is at its earliest stages, it can't be you need a Vannevar Bush approach. You can't, it can't be capitalistic. You just have to let people try to learn things because it's really a learning process, There's the world and it's unknown and we don't understand it and we need to try to understand it. And you can say, what is it good for? And the answer is we don't know because we don't understand it yet. You need to understand it before you can learn what it's good for. So early basic research, it has to be in the government-funded model because and just let people try to learn stuff. There's people have tried to make it more competitive and there's a certain level of that with grant reviews and I don't want to go there yet, but in the beginning it's just learning and it's really hard to systematize that okay, but when it gets to the advanced stage of tech transfer, you really need to leave that model. And I think the government-funded lab model kept it in that structure take too long. So I'll tell you what's much better about the startup. So in the startup model, what happens is there's some people at university, let's say me or maybe you guys, when you get a little older, or maybe you've already started a company, I don't know. But anyway, you have an idea, then you go out and you start a little company. It's its own little entity. And then, so then what happens? So the way you start it is you go out and you get investors. So who are investors? They're rich people with money to burn. And I've met some rich people. That's been one of the really interesting things about starting a company is I've met some actual bona fide rich people who, by the way, are super nice people. They're just people who worked really hard their whole lives and were successful and have truckloads of money and want to do something interesting. So I think rich people will get a bad name because most of them are actually pretty cool. But anyway, so you go find some rich people that have extra money. They want to do something useful with it. They want to make an impact in the world. They just don't want to just stick it in index funds and see what happens. And then they invest in the company. And then you get a bunch of capital. There's some ways to get some government grants, but they're not very big. Mostly have to get private capital. And then you take your idea and you try to take it to market. And this model is so much better because the risk is taken by the investors, which is where the risk should be. In the old model, like the Bell Labs model, the risk was in your phone bill. I mean, why should it be there? So you sort of take the risk and you spread it out all over everybody in the country, even people who can't really afford it. In fact, the poor people, a higher fraction of their salary goes to their phone bill than a rich person. So it's almost sort of you take money equally from everyone, and then you fund R&D, and then there's no particular direction to it, and then you hope something comes out. I mean, it was okay, things happened, but the new system is way better. Because honestly, the risk should go on the investors. And then the founders, the people like me who started the company, we're sort of isolated from failure because I invest my time, but I didn't invest any capital into the thing. And then if it succeeds, honestly, the people who get most of the money is the investors because they're the ones who took the risk, though somebody like me will get some. And then if it fails, it ends. The people who worked there go find jobs somewhere else. Everybody learns something. It's just it's a better system because it's more dynamic, it's more flexible. The risks and the returns are aligned and all the incentives are aligned more properly with where they should be to make things actually work. And yes, I think, if I remember your question, it was really sort of old system versus new system. The new system is way better. As much as I miss Bell and I wanted to work there, I think it needed to go. There, I said it out loud.
They're going to come find you after this.
Yeah, it's a pity, but yeah, the new system is way better. It's more dynamic. I think it's faster. It moves ideas into the marketplace more quickly. It creates incentives for people to do that. I mean, if you work at Bell and you have a nice paycheck and you have a steady paycheck, what real incentive, and you're competing with your colleagues and for status, but there isn't really much incentive to succeed other than that, right? But if you start a company, you're like, this thing better work, and there's financial incentives to do it. Yeah, I think this new system is way better. I wouldn't go back to the old one.
I want to focus on the atmosphere of innovation at, let's say Bell Labs versus today. Mm-hmm. What was it about Bell Labs that made people work on so many interesting problems and have so many interesting innovations that happened in that brief period?
Yeah.
What atmosphere was it?
Wasn't that brief? It was half a century, so.
Right.
Yeah.
But there's so much that just came out in that half century, right?
Yeah.
Just out of that one place. So
Yeah.
what atmosphere was it that was conducive to innovation?
This is just my opinion, okay? So don't take this as scripture or anything, but fundamentally, there's books written about this. People spend a significant amount of time competing with each other for status. It is simply so, right? We try to pretend this isn't true, but it is. And what motivated people at Bell was status. They were competing with each other over who could do the next really cool thing that got everybody excited compared to their. And it was a little bit like academia, because that's kind of how academia is, you know. So, you know, like the academics at the top of their fields are the ones who are publishing the most really highly cited, exciting papers that are written up in the New York Times or whatever, published in Nature or something. And that was sort of what drove Bell. And sometimes that aligned with some really great innovation like Unix. Sometimes it didn't. And there were lots of really boring, silly, pointless things going on at Bell Labs. And I know because I worked there and I did some of them myself. And the reason it was successful because they had so much money. I mean, in the 1960s, 1970s, Bell Labs had this as much science, as much physical science funding as the rest of the country combined. So if they didn't make some discoveries, it would have been a pity, right? So I'm not even sure, I think I'd have to look at the numbers. I'm not even sure that the number of discoveries that were made was outsized for the funding that went in. It might have even been lower than you would expect if you did some analysis of it. Because it didn't exist for innovation. It existed because of some legislation from, you know, almost 100 years earlier. There was a second half of the question, which is how does that compare to the innovation here?
Like today, yeah. Like, do you think you need that sort of atmosphere to facilitate innovation, or do you think how is it different from what we're doing today?
At the U of I, you have the whole spectrum. So we have this background of Vannevar Bush government-funded research where you just work on interesting things and try to learn about the world. And you just have theoretical physicists thinking about topology and whether you can make topological circuits out of aluminum foil and stuff. And no one's really sure why it matters, and there's not that much money in it, but you try to make progress. And then if you just think of something that's really useful, you can quickly shift gears and switch to this other model of going out and getting support through the private sector and then doing it in this other way. And there's even in between, there's this mechanism called SBIR funding, where the government will give you R&D for an early stage company. You guys heard of SBIR?
You got that one, right?
Inprentus went through an SBIR with National Science Foundation, yeah. So that's an intermediate thing where if you have a really early stage company, they'll give you a grant. It's only for R&D. You have to actually really carefully document everything and prove that you only did R&D on it. You didn't do any profit-driven stuff. And they let you bridge that gap. So yeah, I think U of I, the innovation engine here, is the best I've ever seen in terms of just the whole pipeline between early stage, late stage, and in between. Bell Labs had that too. I mean, they had early stage research, they had late stage tech transfer, but they didn't have this change in incentives, you know, where you switch over from curiosity and status, proving you're smarter than your physicist friends, to something that's there to create a return for investors. Mm-hmm. They didn't have that change in incentives as things moved up the pipeline, whereas we have that here. I sound way more optimistic about the future than I thought I was going to.
I love it though. I feel like hearing you say that.
I was ready to come in here in gloom and doom, and maybe it's the warm weather or something.
Perhaps.
Yeah.
You mentioned status, and a U of I person who worked in Bell Labs for a couple of years, for a number of years, was Richard Hammond, and he wrote an essay, "You and Your Research." Have you read that essay?
I have not.
You might like it, but in there he talks about this idea that
I probably would.
That you know, in implied how this status game sort of he doesn't say it like explicitly, but he sort of alludes to it.
Yeah.
That was that. But in your career, how much of that, or in your life, how much of that status seeking, subconsciously or not consciously, do you see yourself engaging in?
Now, in the beginning, it motivated almost everything. You're not going to put this on the internet, are you?
No.
Yeah, no, not at all. Okay, fine. Then I'll just. Yeah, I think in the beginning it was all, look, most scientists at the beginning of their careers, they have a chip on their shoulder and they want to prove something. And to be honest, it's not a bad thing. If it motivates a person to get better and to do innovative things, I don't think we should question why. And the young people who come through my group, they're the same. And I try to encourage them to channel that into positive things, doing good experiments, thinking deeply about what they're doing, and, learning making a discovery and marketing it well. It sounds terrible when you say it, but it's actually, whatever motivates a person to get better and improve,
Right.
I think is a good thing. But you're asking specifically about me. As time went on, you really burn out on that. And you also realize after a while there's no top. You can just keep on going. And at some point, and then you start to get some gray hair, and you realize your life's not forever, and you want to do something meaningful. And I would say, and then, a post-tenure and through Inprentus really kind of adjusted my whole life thinking to more leaving a positive impact on the world. And so I would say I'm not particularly status motivated anymore. It's really more about just doing something, leaving something positive behind. Nobody dies and then sits on their deathbed and says, I wish my H index had been higher. People say, I wish I had spent more time with my children. I wish I had, done something important. So, I spend almost all my time now trying to just improve the world.
I mean, was there like a specific event that made you come to this revelation, or was it more like the time that you have during your tenure? Age.
Yeah.
How do you think that a younger person who does not have as much time currently on their hands can like figure that out? Do you think it just comes with time or experience?
I don't think they should.
Okay.
Really?
Why is that?
I think that if you're young and you're motivated, don't question why. And the truth is, you have to reach a certain level in your career before you have the luxury to be
able to question.
To be able to question it,
Right,
and to
right.
be altruistic.
Mm-hmm.
If you're poor and altruistic, it's pointless because you
Right.
can't help anyone. Actually, Benjamin Franklin used to say, "The empty sack cannot stand upright." You need to have some assets before you can be generous. So I don't know. I'm not sure I would encourage a young person to adopt that point of view too early. I think you need to get to a stage in your life where you're got a reputation and
Resources.
and some financial resources and credibility and people, right, that you can call on for help, who trust you. They talk about having a network. Network means you have a large number of people who've worked with you and can vouch that you're legit and that you know something and you're capable. And then you can call these people because they trust you. And then once you have that, then you can start to think, okay, you know what, I could actually hire a bunch of young people and help them, right? Because then you've got some resources to do that. Yeah, so don't tell anybody our secret.
I thought that was really interesting because I feel like a lot of people will always tell you like you should go chase after something that you think will like make the world a better place, or like try to like reflect, always try to explain like why you're doing something the way you're doing it.
Yeah.
But I feel like when you're younger, it's easy to just like go through the motions of life and not really think like that.
Yeah.
And then like when you hear people like pressure you to think like that, it could be like.
Yeah, I mean, I think I got a lot of this from my kids, especially my younger daughter. She used to say that, her teachers in school would tell her, what they say, find your passion.
Yeah.
And at some point she's like, Dad, I don't have a passion. I just want to prove that I can do stuff. And then I was like, yeah, just go prove it. Don't worry, just go do your thing and don't worry about why. I mean, I don't think we should pressure. I think we should encourage young people to be their best selves and improve. I don't think we need to tell them why they should want to do that. That's up to them. If you have completely horrible, rotten reasons for making the world a better place, who cares? If you're doing it, walk the walk. Don't. Yeah.
Yeah, but it's sort of like, if you read it, you talk about Gen Zs a lot. If you see every college essay, or if you ask anyone why do you want to do it or you want to do it, the number one thing they'll say, I want to help people.
Yeah.
I want to help people. It's such a flaw.
It's not even true.
Right.
I mean,
but, yeah.
maybe for 5. I'm sorry, I interrupted. Go ahead.
Continue.
No, I think it's not true, and it doesn't need to be,
Right.
because you need to help yourself. You can't help anyone until you can help yourself. Like, I could quit my job right now and go be a philanthropist. You guys probably couldn't do that. No one knows you.
If you give me money, I
That's the point. If I wrote you a check for $30 million,
Yes.
then you could do it. So, but this is the point, right? You need to have something to work with.
Some cushion.
Yeah. So So I think people write those things in their essays because they know that's what people want to hear.
Mm-hmm.
But fundamentally, they're just upward pandering to get themselves into the system, which is, look, that's what they should be doing. So I don't fault them one bit for doing it. I fault the people who judge them based on what the expectation that they say things like that. I mean, you apply to college and there's some admissions committee and they want you to sound like you're a philanthropist, and so you tell them that. You can't blame the applicant, right? They're just doing what's going to get them into college. You got to blame the people who on the committee who think that kids should be like that when that's not the way they are. I'm a big fan of deal with the world the way it is, not the way you think it should be. Deal with people the way they are, not the way you think they should be.
I really like that philosophy on life, actually. I
Yeah.
think it's like sometimes things come to you and it's more like a gut feeling that you feel you don't have to like associate a reason with it. But do you think like there's a balance between like finding reason and doing things and then also just like existing through life? And is it important to find that for you?
I'm not sure I understand.
So for example, like when you do decide that like you want to do something, do you find yourself questioning, why am I doing this? Or do you just let it happen to you? Okay.
Never. Absolutely not. I just get something under my skin and I don't think about why. I wrote a paper in Science in 2010 about graphene. And at the time, the entire world was convinced that graphene was a strongly correlated electron system that was going to show all kinds of exotic physics. And this was all over the news and things. Graphene was there was a Nobel Prize in 2010. Mm-hmm. And it was all nonsense because graphene's just a completely boring semi-metal. Did you guys want to talk about materials that I'm not sure?
Wait, yes.
Go ahead.
Yes.
It's a really boring semi-metal that there's been some claims of hydrodynamic effects from Andre Geim that are intriguing, not completely convinced. But for the most part, it's just a nice 2D metal, semi-metal with Dirac cones. And I wrote a paper claiming that it was not a strongly correlated electron system at all, that the thing is actually very polarizable in screens, and that it was just a vegetable. And I never got invited to another graphene conference again. I became like persona non grata in graphene research, and I asked myself afterwards, why did I do this? Because I used to have friends. I had friends in Singapore that used to invite me out there, and then I never got invited to Singapore again. And I asked myself, why did I do this? And I think I just did it to make trouble. I don't know. It was sort of, I think there was a silent majority of people who knew that graphene was a vegetable. I mean, it's a very useful system. You can use it for lots of things, but it doesn't form an excitonic state at low temperature or something like that. It just doesn't do that. So there was a sort of silent majority of people who were just kind of not participating in this. And I just wrote this paper sort of on behalf of the silent majority. I think I just did it to make trouble. It was completely ignoble thing to do. I lost some friends. This is going on YouTube, isn't it?
Do you ever regret it, or are you like?
No, not at all, because it's not. It's not true. I don't know. It's sort of like if you were in a room full of 1,000 people and 30 of them were saying, look at the beautiful elves dancing on the... And there's no elves anywhere, and there's 990 people sort of confused. But there's 10 people excited about these elves, and we're just watching these 10 people get excited, and you just raised your hand and said, dude, there's no elves anywhere. And then those people got really angry with you, but the other 990 are just nodding their heads like, you know.
That's valid.
Yeah, it was a moment like that.
Okay.
And I don't know if I had anything to do with it, but work on correlated electron physics in single-layer graphene kind of stopped at that point. And in 2011, there was a paper by Alan McDonald from UT Austin saying if you took 2 graphene sheets and you twisted them by this magic angle, 1.7 degrees, you'd get a flat band that would be very unstable to strongly correlated physics. And then later people at MIT and UC Santa Barbara did that and saw superconductivity and Mott phases and all kinds of stuff. And since then, the whole field has gone in the direction of these twisted systems. And it's become a much more interesting and productive field. And I like to think I had something to do with that. Maybe I didn't. But after our paper, the field took a U-turn and went in a direction that was much more productive. So, but I might be overrating my own importance by saying that. But
No, you were a trailblazer.
it could be. Well, that was an trail anti-blazer. There was a trail, and I put a roadblock.
And they ended up going
And they
somewhere
went a
lot better.
direction that was much better.
Yeah.
Yeah.
And I want to come back to the materials and physics, but
Yeah.
I see a contradiction in what you said earlier. So
Yeah.
you basically said that you should deal with people the way they are, or understand things how they are, and just go from there.
Mm-hmm.
But in this case, that was not how the things were, and then you decided no, and you were idealistic into some regard of like, that's not it, and this is it, like this is how things should be.
Yeah.
And
You're right. So sometimes I break my own rules. Yeah. You're right.
but it's
You're
like
absolutely right.
it's not meant to put you on the spot or anything. It's just more of a. I agree with you that there are times where it's just sort of like being a scientist. Like you can question everything and believe everything.
Yeah.
So you have to be in the middle, right? And at times, you find this innovation or you set new trails when things should be this way, but also that causes a lot of trouble and headaches because you're not going with the way of the system.
Yeah.
How do you make sense of such things?
It's super hard. It's really hard to know what to do. Sometimes you have to go. If you swim against the current all the time, you never get anywhere. If you swim with the current all the time, you never change anything. So it's really hard to know what to do. You have to be somewhere in between, and it's really hard to know when to go with the current and when not to.
You gotta go perpendicular to it.
Sometimes, yeah.
1.6.
Well, that's right. But there isn't, what angle, right? Is it 90 degrees or 30 or 10 or 172? It's so hard to know. So I don't know. I sometimes, sometimes I write contrarian papers. Sometimes I've written a few times the paper that everybody wanted to read. And it just came out and immediately got zillions of citations. I've done that a couple of times too. So I would be going with the current. Yeah, if I had a formula for how to do science, I would have told you at the first 5 minutes. And I don't have one, and I don't think there is one. It really is, there isn't one way to learn, and there isn't one way to make progress. And you just gotta wing it. Yeah, experience counts for a lot. And I'm probably gonna go to my deathbed not knowing exactly what I should have done. And that's just true for everybody. You just gotta do your best.
Does social acceptance matter to you?
We're all telling the truth now, right? Absolutely. Yeah. But not 100%. I mean, I don't mind being an outcast if needed. Well, social acceptance from who?
Like in terms of, let's say your papers, for example, right? Like did a badly received paper
Yeah.
want you to write a paper that would have been less controversial, just like more widely accepted by everyone?
Yeah, it sucks. You pour your energy, and I've done that. Poured my energy and creativity into some paper, and it just gets trashed. That has absolutely happened to me. I'll give you an example if you want, but yeah, it's gut-wrenching. It really is.
Yeah, could you give the example actually?
Yeah, okay, so in in the early 2000s, there was a big nationwide effort in studying electron dynamics with ultra-fast laser techniques. And you guys know about time-resolved lasers and Ti-sapphire lasers and this sort of thing. Okay, anyway, so one way to study materials is there's a technique called pump-probe spectroscopy. You take a material, you take a laser, and you make a really fast pulse, and you blast the sample, you perturb it, and then it undergoes some dynamics. And what's the sample? Could be a molecule or a solid or anything. And then you blast it again, and you measure something: the fluorescence, reflectivity, the birefringence, Kerr effect, all kinds of things. And then by varying the time delay between these two pulses, you can get an idea of how this object evolved in time. So it's a classic way of measuring dynamics. There was a Nobel Prize, Ahmed Zoel at Caltech in the 80s, used this to measure potential energy surfaces in chemical reactions. It completely transformed chemistry. There's people on campus here still doing this stuff and setting new directions and so on. There's another way to study dynamics where you study it in the frequency domain, where you just shine light on the material with some well-defined frequency, and then you scan the frequency and you watch how this thing evolves, like its reflectivity evolves in frequency. You guys taken math?
Yes.
Have you ever heard of a Fourier transform?
Yes.
Okay, so if you have a function of time and you Fourier transform it, you can write as a function of frequency. Every function of frequency can be written as a function of time. Every function of time can be written as a function of frequency.
Right.
So in the early 2000s, I thought, I wonder if you could get all this. So I left this stuff to state out. You have to edit this part out. But anyway, in the early 2000s, there was this effort to study materials and molecules in the attosecond regime. So when Zoel did time resolve, it was all using femtosecond lasers. That's kind of the time scale of chemical reactions. So if you want to study electron dynamics, then you need to go even faster because electrons move really fast. So the plan was to make attosecond lasers using what are called high harmonic generation techniques. I could talk for hours about that. Very cool. And phone call. Yeah, so anyway, so there's a lot of new money and investment going into these attosecond lasers, and there's this mathematical principle that if you have a function of time and it's very fast, that in frequency, if you Fourier transform the thing, it's really spread out. And so I had this idea, I wonder if you just measured the frequency domain response of this material, if you could Fourier transform and get the time dynamics that way. And I did this. I was a postdoc at Cornell. This is like 2001 was sort of the time frame. Actually, when did the paper come out? 2004 when the paper came out. Anyway, so I did an experiment on liquid water, measured its frequency response over just a huge range of frequencies, like 100 electron volts. And then did some math and figured out I could actually reconstruct the time dynamics of the thing with attosecond time resolution. I wrote a paper in PhysRev Letters with some other people at Cornell that had electron dynamics in water with attosecond, was 21.6 attosecond time resolution, which was like 100 times faster than anybody had done with attosecond lasers at the time. And I thought everybody was going to get super excited. And they were so mad. The laser people were so angry. Yeah, I was persona non grata in that field for a long time too. I was an assistant professor here at around that time, and actually this famous guy at Stanford actually told, I had a research grant from the Department of Energy to do these kinds of measurements, and this really prominent scientist at Stanford told my program manager at DOE, hey, this guy is completely full of malarkey. All the stuff he wrote is wrong. He doesn't even measure dynamics. He's just measuring some autocorrelation function that doesn't even tell you about the time dynamics. And he just basically trashed me to my program manager. And my program manager called me and was like, is this true? 'Cause I almost lost my grant because basically, he sort of tried to torpedo my group's funding. Yeah, so what was the question? It was about
a time you faced criticism in like the field and how you dealt with it. Or,
so I got lots of criticism for that paper.
How did you feel about that? Because I'm sure you like put your heart and soul into it. Now
I did.
there's like professors.
I invented a whole new mathematical way of analyzing X-ray scattering data for this paper.
Yeah.
And it felt very unjust because everything I had done would stand up if anybody sat down and they looked at the arithmetic, they would agree with all the steps. So everything was correct. So you might say, why was there such grave opposition? I don't know. I think people are humans. Scientists are humans, and they had an agenda, and their agenda was lasers, and they had research grants and students and an agenda built up around that, and they don't want to see a threat to that because they have their plans. And if you write a paper saying, look, I can get 100 times better resolution just doing this simple thing, it just torpedoes what they're doing. And that was a big eye-opener for me because, I was sort of, science is not just a pursuit of truth. There are human consequences to the things you publish, which doesn't mean you shouldn't publish them, but you can get negative reactions for all kinds of reasons besides being wrong. And so what did I do? I went to bat. I didn't go to war, but I stood up for myself. I wrote more papers. I wrote paper on excitons and alkali halides and other things, and said, look, it works, and eventually built up a little
community,
not a following. Yeah, it didn't get picked up by other people who started doing it too. But I made a case for it and convinced many people that it was correct, and left it at that. And then in 2008, I think I wrote my last paper on that. 2010, I wrote my last paper using that method. I wrote a little review article about it, and then I stopped. And I just let it go. And I never did it again.
It sounds like a lot happened. I feel like going through that experience is like very...
It was rough.
Yeah. How would you, so I know like a lot of students on campus are probably going through a lot of experiences where their journals are getting rejected as well. Like how would you recommend like students or like professors to deal with like rejection time and time again?
You've got to have some chops to make it in science. And you've got to have chops to make it in life anyway. So you're just going to have to get some chops. You've got to just, every time they knock you down, you get up and you keep going. And if they knock you down again, you get up and you keep going again. And if it's 100 times or 1,000, you keep doing it. And you don't give up. That's the way you do it.
Yeah.
And then eventually you will strike gold or something. Eventually. It's all determination and patience, and that's the most important thing. I think people take setbacks too personally and too hard, and sometimes people give up. And I think that you people need to have more determination and not get discouraged so easily. And it's hard when you're young, because you may submit your very first paper ever, and then it gets rejected. And then it's, I mean, I've written 100 some odd papers. If one gets rejected, I'm like, yeah, whatever, I don't care. But to the student, it's their first ever paper. To them, it's like the end of the world. It's 100% of their papers that have been rejected. It's really hard for them to just say, whatever, I can keep going, because they've never succeeded before. Mm-hmm. You never know till your first success that you can do it. And success is always on the other side of failures, right? Fail, 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 and then you succeed. But you've got to get through those failures once. And once you do and you succeed, then you're like, okay, I think I can do this again. And then after a while, the successes start building up, and you lose track of the failures because there's so many more of them, and then it's all fine, then you're okay. But yeah, it's rough in the beginning. I don't want to be young again. I wouldn't want to go through it again. Glad you only have to do it one time.
Oh gosh.
That example that you mentioned, it's also funny, because it goes against what you said earlier about...
Did I contradict myself again?
No, because it's funny, because, you were like, go against, how things are, and that example, you went against how things are. So it just sort of how perspective changes as you grow. As you grow. So that battle that you had, is that what led to the technique that you developed? I think it was called the soft
Soft X-ray diffraction.
No, that was different.
Okay.
That was actually much more. Okay, good. Just so you know, I'm not a total contrarian. Soft X-ray scattering, I actually started with a professor in the Netherlands named George Sawatsky, a really famous guy who has since moved to Vancouver. And that was a technique for studying valence band order in all kinds of correlated electron materials. And that was the opposite. So there we had a paper in Nature in 2004 where there were it was on these materials called spin ladder materials. They're basically copper oxide. They're sort of perovskite materials where you have copper oxide chains that form these ladder structures. And there were some theorists. There's a theoretical technique called the density matrix renormalization group, which was invented by a theorist at UC Irvine named Steve White, brilliant guy. And he and this other theorist named Ian Affleck had been studying these ladders theoretically with this DMRG technique. And they predicted that they would form charge density waves. So these ladders you put electrons in them so that they could be conducting. And then the electrons would form a crystal. There's also another name for that. It's called a Wigner crystal. It's where electrons form a crystal in a solid, sort of like atoms do in a... and we use these resonant X-ray techniques, and we actually saw these crystals in these spin ladder materials. And they had very similar phenomenology, what had been predicted by these DMRG guys. And they formed on these rational fractions that were similar to the ones that they predicted in these simulations, and the paper sailed through Nature, and it got tons of citations, and that's what got me hired here. So it was sort of a thing where everybody wanted that to happen, and then with the experiment, and then what everybody wanted to happen happened, and the paper sailed through in the first round of review. And then I got a job. So that's the exact opposite of those other things, right? So what was the point of that story?
How the story of the soft X-ray.
Yeah, that was a technique that really sort of showed what people wanted to see. So at the time I thought, hey, look at me, huh? Boy, I sure know what I'm doing. But it was really just luck. I mean, if we had seen something that completely contradicted what the DMRG
People
guys
would have been
predicted,
mad.
then everybody would have been mad. I mean, you don't get to decide what nature does. You just observe it and you report it.
So true.
And you can bias it a little bit, but by emphasizing certain types of measurements or something. But nature does what it does. Yeah, this is the other big thing is luck plays a huge factor in your life. Enormous.
3 questions.
Yeah.
First, what do you think you got lucky in life?
Where do I think I got lucky?
Mm-hmm.
Yeah.
Second, I think one of the things that has started happening today is like people publishing false papers,
Ooh, that's a good topic. Yeah,
right?
Yeah, one of my
So,
favorites. Yeah.
And it can be tied to that the topic around status and like getting that appreciation or whatever, right? In the community. So your thoughts on that? We'll touch upon it. And the third is which of your papers got rejected? Like we've only talked about the ones that like made it
Yeah.
and got bad or good in the public eye, but
Yeah.
like which of your papers that you think would have been good but got rejected?
Okay, the first question was about luck. Luckiest thing for me was my spouse. Her name's Cindy. We met on the bus.
What's the story?
That's the story.
But-
Yeah.
Like, where were you guys?
They-
We were students.
Who approached who,
We
yeah.
were students here. This was in 1995.
You were here around the time, yes, I think so.
Yeah, I was a student here for a few years before I started working with these Bell Labs people.
Right.
And I met her on the orange bus. This is
Orange?
before Tinder.
We didn't have orange.
The orange
We don't
bus
have
was
it,
Tinder.
Yeah. I just thought she was cute. I started talking to her.
Did you?
That
What was
was
the
it.
opening
Damn.
line? You're like, hey,
I'm not telling you.
Cindy, I think you're cute.
No, it wasn't that. No, I'm not actually. So it was.
Let's scatter some X-rays.
not-
Wait,
telling
we
you.
cannot publish this.
I'm not telling you. No, I started talking to her. She was reading some biological paper, and I thought, okay, she probably is bright. And I started talking to her. And yeah, I'm not going to embarrass myself with it because I'm not very good at this kind of stuff. But anyway,
You didn't need to be good. Just one
I
time.
didn't need to. She was better. So, yeah. Yeah, that was luck. I was raised in a single parent family, so I had a mom who had to double as a mother and a father, and she was really good. So that was luck. So what was the other part?
And then wait, before that, what's the story of going to Netherlands and having the kid either there or here? I don't know.
Oh, we had one daughter there.
Okay.
Came
Oh,
back
wow.
here, had another one.
Right.
Yeah. Was that part of the question?
Like why going? Just why going to Europe? I mean, that's not like
No life plan. Didn't know what to do. My life plan was shattered.
Was it after a bad paper?
Oh, you were going to ask what happens to your papers.
No, we'll get to that.
We'll
We'll get to that.
we'll
But
get
like,
to it. We'll get to
Papers. Why do we move to Europe? I wanted to go work at Bell and it closed. I didn't know what else to do.
yeah.
And this George Sawatsky guy, I met him at a conference, a Gordon conference, and I just thought he seemed cool, and I wrote him an email, and he made a few phone calls and checked up on me, and then he hired me, and we moved abroad. I had no idea why. I didn't have it wasn't some. Here's the other thing. I know young people tend to over plan a little bit. They're like, oh well, I want to be doing this when.
Right.
So they're like, well, I need to major in this because I want to do that, and it doesn't work. Sometimes you just have to take a leap of faith and try stuff.
Sure.
Because you're going to be alive a lot longer. The other thing I've noticed is young people tend to think that they're going to die of old age when they're 26 or something like that. They need to have their whole life.
Who does?
I don't know. A lot of young people, they're like, oh, I've got to do this and that and the other thing. And I'm like, you're 22. Why are you?
I mean, I feel that.
You do?
I mean, a lot of people in my age feel that way because I think they think
Because of
like
climate
once you
change? Or
maybe, but I think it's
Maybe.
more just like when you leave college, you think that like your life like starts and ends there?
I mean, I didn't have any idea what I was doing until I was in my mid-30s. You know, your life is really long. I mean, yeah, you're not going to have the corner office and the prize when you're 25. And if you did, what would you do the rest of your life, right? Anyway, so yeah, I mean, just go do stuff that's cool. I just thought it would be cool. You live in Europe. I'd never lived anywhere, another country. I grew up in Texas. Europe was the most unlike Texas you could possibly imagine. So I just wanted to try something different. So we went.
What was the biggest culture shock going from Texas to Illinois and then to the Netherlands?
Ooh, actually, the shock from Texas to Illinois was much bigger than the Illinois to Netherlands.
Wow, that's crazy.
The Illinois to Netherlands was fairly seamless.
Okay.
Texas to Illinois, I mean, people swear a lot more in Texas. So I had to learn how to talk again. And I think people, yeah, I don't know, Texas is a lot more, I think it's a lot more aggressive and status conscious. You know, the South is very laid back and easygoing. Texas is not like that at all. It's very competitive, very status conscious place. People really care about money and cars and clothes and Illinois was a lot more civic-minded and
Mellow.
Yeah, well, not just mellow, but people worry. Midwesterners want to be good people, right? They don't necessarily, you know, and they sort of make an effort to be like that. I'm not saying Texans are evil or something, but they're much more status conscious and aggressive. It's sort of like New York culture in the South, kind of, you know. So, yeah, Illinois was an adjustment. And I think that it's much more important here to be polite to people, which is really important because I like people to be polite to me, so why shouldn't you be? So once I adjusted to Illinois, Europe was pretty easy because it was kind of the same. That was sort of my experience. So, did that answer the question? I forget what the question was.
Yes, the next thing he said was fake papers.
Fake science. Let me silence this thing again. Yeah, where do you want me to start on that one?
Whatever comes to
Hendrik
mind.
Schon, the false discovery of a new element at Berkeley Labs in the early 2000s was fraudulent.
Let's start with that.
Well, I know less about that. I can tell you about Hendrik.
Sure.
He was at Bell Labs as a postdoc. Do you know who Hendrik Schon was? Really? Okay. When I was a grad student, there was a postdoc at Bell named Hendrik Schon. He was from Germany, Konstanz University, I think his PhD. Came and worked with Bertrand Batlogg. He was this brilliant Swiss physicist, materials transport guy, studied superconductivity. And Hendrik came and they were making field effect devices. So, you know, a transistor is there's different kinds of transistors, but an FET is basically a quasi-2D conductor where you have gates, and if you apply a voltage, it creates a potential and you can switch off the current. So that's a field effect transistor. Mm-hmm. And so the idea was to gate things that aren't silicon, to make thin layers of other stuff, pentacene, spin ladder materials like, you know, got me hired here. And so what they did is they were taking thin films of stuff, putting gates on them, and then putting charge into them. And then there's all this interesting stuff that can happen. I mean, if you have silicon, you can switch it from an insulator to a conductor with a gate. If you take a polymer, you can switch it from an insulator to a metal to a superconductor, or from a charged Wigner crystal phase to some exotic other thing. And they just started discovering all these phenomena, and they found superconductivity in pentacene, which is a polymer, which is insulating. But if you put charge into anything, it's going to become conducting. and I think they saw superconductivity 117 Kelvin. I mean, crazy high TCs. And these guys just started pumping out papers like nobody's business, and Science, Nature, PRL, APL, everything. And it was astonishing. And I remember watching Hendrik from afar, and he was a brilliant speaker, good-looking guy too. I mean, so he was like the whole package. He was like better looking, smarter, more productive. It was like everything was better about Hendrik. I mean, he was like a god. And his boss, Bertram Batlogg, was brilliant and charming and flying around the world on the lecture circuit. And then Hendrik they were nominated for a Nobel Prize. Which they were going to get. And Hendrik was hired as a Max Planck director in Stuttgart, which is kind of the Queen of England of physics jobs. Is a Max Planck in Stuttgart director in Stuttgart. And but nobody had reproduced any of their results. And I remember visiting Princeton and giving a talk there and talking to Planong, this really prominent physicist there, and he was trying to replicate some of their measurements, and he couldn't get the gates to stick to the plastic, if I can remember. I think as he was working on polymer at the time. Maybe it was a different system. Anyway, and I remember him saying to me, yeah, we just can't get the gates to stick because we don't have the technology that they have at Bell Labs. And I just thought, yeah, okay. Because Bell Labs was Bell Labs, right? Nobody ever questioned anything that came out of that place. And this was kind of in the sunset era. And then Lydia Sohn, a professor at Princeton, and Paul McEwen, a guy at Cornell. I don't remember the exact sequence of steps. We're working on one of these systems, and they noticed that the noise pattern was identical in two different papers on two different materials. And I don't know if you know anything about random number generators, but they're not actually random. A random generator or number generator always requires a seed. Mm-hmm. And then the sequence of numbers that comes out after that is deterministic. So if you use a random number generator and you don't change the seed, you get the same pattern of noise on top of your data. And so they saw that the noise pattern, there was 2 points, remember they went up and then they went down together. One was on this polymer, another one was on some other material. And they said, couldn't be, right? And turns out it was all fake. Not only were the data fake, but there were no samples. So in the time, I read these papers really carefully. When I was doing the experiments on these spin ladder materials, 2004, right? And so Hendrik Schoen had a paper on spin ladders too, strontium-2 copper 03. And I studied that paper carefully because it was similar material to what I was studying, and he put gate electrodes on them, and he saw superconductivity, and I read that paper, and it was brilliant. I mean, and it was so realistic, and it talked about how they had to use RF sputtering to put the gates on because they were made from an oxide, and they were insulating. You can't sputter insulators with just DC sputtering. And there were junction capacitances, like every detail was in there. There was no samples, nothing. It didn't exist. There were no materials, all fake. There's books written about this. Anyway, so the whole thing blew up, and
How much time was it before they published it and it blew up?
I think 3 years.
3
4
years.
Yeah. Enough time for there to be a Nobel Prize nomination. So what was the question? It was,
Wait,
does this happen?
Yeah, so the guy was, great, whatever. Why was he doing this? Like, do you know anything?
That
about-
is a wonderful topic. That is the question.
Like, you know, or like.
Why would a brilliant, young, good-looking, more than me, articulate physicist with credentials and prospects and a postdoc at Bell Labs do this?
It's like a movie.
I don't know the answer. I think that I think that not all people have the same understanding of what it means to know something. And I think that's a fundamental problem in many things. Like, how do we know this bottle of water is sitting on the table, right? Like, if I take it away, and if there was a person in the room who said it's still there, how would you convince them it wasn't, right? You could wave your hand and they could say, well, it's still there, but your hand goes through it. Not everybody has the same understanding of what it means to know something.
Right.
And I read an interesting expose on Hendrik, and it was based on an interview. And one of the things that people asked him, why did you do this? And this article, which I should go find and not just whimsically cite in an interview, it said that he believed that he was telling the truth because he thought that if he had made these devices that they would have done what he had said. Because it was believed that pentacene would be superconducting by certain theorists. And so he assumed that if he did make a pentacene FET and put a gate on it and got enough charge in it, it would be superconducting. And so he thought that because he was simply representing what would have happened if he had made the devices, he was actually telling the truth. So I don't think he knew he was lying.
But he was still lying through numbers, right? Like, it's still okay.
Where do you get 117
Right.
Kelvin TC?
Right.
Never believe it if it's a prime.
Why is that?
Prime numbers sound more
I mean, it's
random,
a factor of 3.
right? Oh, is it?
And 9.
It's actually a multiple of 3.
Yeah.
7.
And 9.
But anyway, there's certain numbers that sound more random than other numbers, right? So if I said, 37% of people think that the sky is green, you'd say, but if I said it was 25%, it would sound more like I made it up.
Right.
Right.
There's some numbers that
So there's certain numbers that sound more random. Yeah, 170 is not. I knew as soon as I said it was a prime, I knew I made a mistake. But it's also multiple of 9, I think.
Yeah, 3 and 9.
Yeah. Anyway, so the number's suspicious. Anyway, there are more cases like this, some in the news recently, which maybe I should not comment about if you're going to put this on the internet. So let me just not go there. But there's a thing going on right now that's probably in this category.
How did these papers even get published?
Well, okay, this you back on the record. How do these papers get published?
Because if they end up not being right, like, does that mean the committee did a bad job reviewing it?
No, because peer review, you simply look at the evidence presented,
Right.
ask if the conclusions drawn from it are
Reasonable.
are substantiated
Mm-hmm.
by the data, and then you ask, do they have enough data, right? If is it not substantiated, is there some problem with the reasoning? Did they misinterpret the results? This is the kind of thing you can do on peer review. You can't know in peer review if the data are fake. There's no way to know that.
Right.
It's all based on on trust that the people are truthfully representing the work that they did.
Hmm.
So peer review is not perfect, right? So what recourse do we have against people who just completely make up their data? The recourse is when other people, so real science, what happens is other people start to use it for stuff.
Right.
So like when Bernards and Muller discovered superconductivity in the copper oxides, people quickly started finding other copper oxides that were superconducting. And then they started taking those ones and making magnetic tapes and trying to make switches out of them, and it grew. If a result is not reproducible, it dies.
Right.
And that's fundamentally the recourse against anything. And then things that die, they just get forgotten. So there were big discoveries 30 years ago that were in the news at the time. And I mean, maybe they weren't wrong, but no one ever reproduced them, and they never got used, and they've been forgotten. So I think that's the ultimate recourse. So I think, these things take care of themselves eventually.
How do you think the scientific community can like prevent things like this from happening in the future?
Can't.
It just happens.
It just happens. There's nothing I don't think there's anything that needs to be done. Simply let them do it, and then let them. People will do this, and then they will experience the consequences. And that's it.
Survival of the fittest.
I don't know. Yeah. In the long run, honesty is the best policy. I hate to sound old-fashioned, but it really is true. If you want to have a long career doing anything, you have to be honest. I don't care if it's in science or business or medicine or whatever. Your long-term success depends on people trusting you. And they only trust you if you tell the truth. So it always comes back to bite you. It may take a long time. And when you're young, you'll see people just take off into the stratosphere and leave you behind by lying. And you'll think, this is so messed up. Because I'm sitting here being honest, and then they're getting all the attention, and it's hard. But if you wait, they come down and yeah. So I don't think anything needs to be done. There are a lot of problems in the world that you don't have to fix. You can't fix them. And you don't need to. You just let things play out and it'll be okay. And this is one of them.
And at some point, some young scientist named Peter might come and tell, that's not how it is. I'll fix it.
Yeah. Right. Well, that's what happens. I mean, other people will start to try it, will do it and say, look, I didn't get this. And they'll do what I did. I'm not the only one who does things like that. Lots and lots of people do that. It's part of the whole scientific enterprise. We go after each other. Anybody who writes a paper, especially if it's a high-profile paper, they just come after you. And the way they come after you is they check it, right? And if you're wrong, then they right? They'll what will they do? What do you do? Publish a paper and say it was wrong. Then it's embarrassing. Yeah, so we don't need to police scientists. They police each other.
What happened to the researcher?
Hendrik. I don't know. Because we could open up Wikipedia and look. I heard that he was driving a taxi at one point.
Really?
But eventually got a job at a company somewhere. I heard that he was living in China, but I don't know what he's doing now.
It's like a temporary high, and then just...
Yeah, maybe that was all he wanted, was 15 minutes of fame and then move on and do something else. I don't know.
Sounds like karma. I don't know.
Yeah. What goes around comes around. But if that's what he wanted, I mean, who am I to judge? I don't know why he didn't just go on American Idol or something. Maybe he couldn't sing.
He had the looks and the...
He had the looks and the charm. Might have had a good shot at something like that.
When you look at the field of condensed matter physics, what are you excited about? Where do you think the future is, and what are sort of the important problems?
Well, condensed matter physics is very herd-minded. We all tend to we go through these phases where everybody kind of does one thing and then they switch to something else. So, in the early 2000s, nano was everything, nanotechnology, and then in mid 2000s to 2010 was graphene heyday. Nanotechnology became boring and everybody's doing graphene. And then a few years later was topological insulators suddenly became like the elephant in the room. Everybody was doing topological insulators. If you were doing graphene, you were old hat. And then now it's twisted bilayer graphene, where they take these two graphene sheets and rotate them by Alan McDonald's angle, and cool things happen, and tons of people are doing that. I've been alive long enough. I'm starting to ignore these things, and I'm thinking about what are the big questions. And the answer is I don't know. But so you're asking sort of you said condensed matter physics, right?
Which is, sort of your field.
Yeah,
so
condensed matter.
What are sort of this, big questions that you're thinking about?
I think the most important problem in the field is the strange metal problem, which you guys have probably never heard of. So metals are things like copper and aluminum. Electrons can move freely. They have partially filled valence bands, so electrons can freely move.
Right.
And you can measure the properties of electrons with lots of techniques, specific heat. You can use photoemission to measure the band structure. And they adhere to some general principles. There's a theory called Fermi liquid theory that more or less encapsulates how electrons behave in metals. And it's based on the idea that if you look at a metal in aluminum, it forms what's called a quasi-particle, which is an electron dressed by some excitations of the electrons around it that forms some kind of composite object that moves pretty much like an electron, but maybe with a different effective mass. And so that's a normal metal. Strange metals are metals, but they don't seem to have any connection to quasi-particles at all. And I'll give you an example. So, in a normal metal, there's a scattering rate. So if metal has resistance, and the resistance is because these quasi-particles are scattering off of each other. And you can measure, just from the resistivity, you can measure the average time it takes for an electron to scatter off another electron. You can measure the average distance, the mean free path an electron travels before it hits another electron. These are sort of basic properties of metals. And the mean free path depends on temperature. So if you heat up a metal, the mean free path will get shorter because things are moving more and the resistivity goes up and the scattering rate goes up and the scattering length goes down. Okay, there's a limit called the Mott-Yoffe-Rego limit, which is the maximum that the resistivity can be. Because once the mean free path of an electron becomes equal to the distance between electrons, the resistivity cannot possibly go higher. So resistivities in normal metals saturate, and the limit is, as I just said, it's the Mott-Yoffe-Rego limit, MIR limit. And there are lots of normal metals. Actually, copper and aluminum melt before you can ever get to it, but there are other metals where you can reach it, and they do in fact saturate. Strange metals don't do that. The resistivity in many of them will blow straight through the Mott-Yoffe-Rego limit and exceed it even by a factor of 10 in some of them. And what that means is that an electron will scatter 10 times before it reaches the next electron, which is ridiculous, because how can a thing scatter before it encounters anything else? And they do many other odd things, which I could get into. That if you just measure the resistivity as a function of temperature, it's just linear. It's a line, which is odd. In a normal metal, it's supposed to go like T squared. Having linear resistivity doesn't mean anything.
Mm-hmm.
So this doesn't seem like something that you'd start a company based on, right? But the whole structure that we have for understanding solids breaks down in strange metals. And we really have absolutely no idea how to even describe the state of matter. And it happens in a lot of things. It happens in a lot of different categories of materials. Some of them are superconductors, some of them aren't. But there's talk of strange metal phases and neutron stars and all kinds of stuff. I think this is a thing where there's really going to have to be a revolution in thinking about solids to make progress on it. And when that happens, there's going to be a new branch of science that appears. And it's probably going to be relevant to a lot of things that aren't just these weird metals, probably something else too. And it's going to require some completely new starting point for describing materials. And coming back to my point about string theory earlier, where I unfairly said that string theory was useless. Did I say that?
Mm-hmm.
Actually, the string theorists are sort of leading the charge on the strange metal problem, using holographic techniques that are based on quantum gravity. So some of those techniques that they developed mathematically that were useless, I think actually might be, they were developed for cosmology, but I think they may actually be useful for studying these strange metal materials. So I brought this up on purpose to not unfairly dump on the string theorists, because often you develop machinery and it's not useful for what you thought you were going to do, but it's useful for something else. So I think this is the problem. This is it. If you don't care about tech transfer and you don't care about getting papers in Nature and you just want to know what's going to transform human thinking, it's this thing. That's my opinion. Maybe I'm wrong. I've been wrong before.
So you say a new branch of science, like a whole new physics, or?
At least a new theoretical framework for understanding many body collections of particles. Yeah, there's going to have to be something completely new.
How are you positioning yourself to be at the? Because ideally,
we're doing our share of experiments on strange metals, and they are really weird.
As the name suggests.
Yeah, really strange. In my group, we're actually studying the plasmons in these things. You guys heard of plasmons? About sound. Sound is it's a wave in the density of something, right? If I hit a material, I'm actually exciting acoustic phonons, it turns out. There's the electrons in a metal can form their own sound wave. But electrons are very light, so it's very high frequency, and that's called a plasmon. It's like a sound wave in the electrons, and it moves very fast, so it doesn't mix with regular sound. And there's another issue, which is electrons are charged, so they're sit at really high frequency, which is actually turns out to be related to the Higgs effect. So that's another topic. So normal metals have nice plasmons. Like aluminum, there's a plasmon. The plasma frequency is 17 electron volts or something, and you can excite them with high energy particles, and they'll propagate good distance. And it's just like any kind of sound. Strange metals, they don't have plasmons. There's kind of a resonance there at small momentum, but they don't propagate. It just fizzles. And we've been measuring what they have instead, and it's a lot more like sound wave in like a heterogeneous medium. If you take some styrofoam and you ask, sound can't propagate through certain media. There's all these, people make sound insulation. It's porous and has all these holes and things that scatter, so acoustic phonons can't really propagate. It just absorbs it. So strange metals are sort of act like sound insulation for plasmons. They absorb the excitation instead of letting it propagate. And then they have this thing where they violate the Montt-Joffe-Regel limit. I think the way people normally think about them as an electron doesn't really have it really doesn't have any identity as an electron in a strange metal. There's this strongly correlated soup of entangled particles, and if you drop an electron in it, it sort of fractionalizes and turns into some other kinds of entities that are related to an electron but are somehow distinct. And the physics of the system is described entirely in terms of some other degrees of freedom that aren't electrons at all. So some kind of fractionalization going on. But nevertheless, you hook wires up to it and you can run a current through it, so electrons somehow get from one end to the other. If I'm getting you confused, then I hope I'm succeeding, because I don't think anybody understands most of this. So that's the problem.
Is that related to the excitonium from 2017,
Oh, that was
2017 or completely
No,
different?
that was another. That was our paper. See, you saw that.
Yeah.
That's on YouTube. Excitonium is a Bose condensate of excitons.
Okay.
There was a material called titanium diselenide. It's a transition metal dichalcogenide. People thought it had a Bose condensate of excitons since the 70s. And we wrote a paper showing that it does. And it made everybody super happy. And it went into Science and has zillions of citations. So it's an example of going with the flow and not against it. Yeah. Which was completely an accident, because it could have ended up not being one, and then I would have written the thing that got everybody mad. But it turns out it does actually have that. So we were able to write a paper that made everyone happy.
Last week we were talking with a theoretical physicist, and the thing he said...
Oh, Philip. Was it? Oh, no, sorry.
No.
Okay.
But we love to know who that is.
Okay.
But so we're talking to a theoretical physicist, and one thing he was saying that, the thing, we come up with these theories and everything, but is the instruments that allow us to, either prove or disprove, or well, I guess not disprove, but to sort of know what's actually true or not true. In your case, you develop a lot of techniques and instruments. And
Yes.
So I guess one question would be, what's that all about? How do you build these things that are so, from the outside, they seem very complex and very precise, and it's a whole new world there.
How do you build it, or how do you decide what to build?
Both. You could know what to build,
Yeah.
which is already hard enough, and then
Yeah.
how to even build a thing is just another level
Knowing
of
what to
complexity.
build comes from experience, and it comes from trying to understand things deeply over decades and realizing there's a certain piece of information that was missing. That's how you get the idea. So it's again, patience. Once you figure out and actually here's the thing, in science it's a huge enterprise, and it's very old, and there's bazillion numbers of, I don't know how many scientific papers there are in the world. And when you're young, every time you have an idea, you realize it's already been done in the 1960s in Russia or somewhere. As you get older, you start to realize just how many glaring holes there are in things that have been missed. Really obvious things that should have been checked haven't been checked. And you start to see the holes. And then it becomes sort of obvious what needs to be done. So once you decide what to do, how do you do it? You have to build a big experiment. And that's not easy, because you have to go get money for it, because it's very expensive too. So how do you do that? That's that's the job. It's kind of like starting a company. You have to go out and get people excited and fight like crazy and get resources. It's not simple. So the experiment we've done the excitonium, which is also where we've been studying these strange metals, is called an EELS. It's an electron energy loss spectrometer.
Mm-hmm.
It's a way of measuring collective excitations. You basically take a material, you shoot an electron at it, and it disturbs the density. It's kind of like skipping a pebble off a pond. and we're studying the ripples. That's basically the idea. And so where did that come from? So you might ask, well, how did we build that? That was a 10-year project, and it cost probably $3-4 million over the scale of a decade. And how did I do it? I'll tell you how I did it. Can you put this on the internet? Maybe. You're going to let me look at this first, right?
Yeah, the whole thing.
I was part of a big DOE center with some people at Brookhaven and Argonne, and I was able, at that time, at the end of the year, if DOE had extra money, they would send you. They'd give you money for instrumentation. I got some equipment from that, and then some fancy school on the West Coast tried to recruit me. And I went to the U of I and I said, give me some more money and I won't go. And I got some money from the U of I. Truth be told, that's what happened. And then I was between those two things and some other $50,000, $60,000 at a time here and there, was able to cobble together a prototype, get some preliminary data. And then the Gordon and Betty Moore Foundation launched a huge national program called the EPICS Initiative, which is on studying quantum materials with new techniques, and it was sort of perfect timing. And I called up the Moore Foundation, I pitched this to them, and they liked it. And they gave us $1.8 million over 5 years. And that really lit the fires under the thing. And we rebuilt the whole instrument with this EPICS money. Do you know about the Moore Foundation? Gordon Moore founded Intel, right? Mm-hmm. Moore's Law, billionaire. He put his personal billions into this foundation to start science, and we got a bunch of that. And we were able to build this thing up, and that's where this excitonium paper came from, and it's what we're using to study these strange metals. So yeah, how do you do it? There's no formula, and you often have to cobble money together from different sources using whatever legal but aggressive tactics are necessary to get it to work. And yeah, you have to be old to do it. You have to have lots of friends and lots of credibility and have been through many cycles of failure and had enough collective trust from the whole community to do something like that. And a lot of luck. Yeah. If Moore hadn't come in, I don't know how we would have done it. That whole excitonium thing probably would not have ever happened. So they're kind of the guardian angels of condensed matter physics as far as I'm concerned.
What advice do you have for young people either in high school or college about how to have a life that they can be proud of, do work that they think that they want to do and that it's important? What would you tell them? What do you tell your daughters?
I let my daughters just do what they want. I just make coffee and give rides whenever they need one. What would I tell young people in general? I would say, I guess going back to what we were talking about, don't worry about why you want to do what you want to do, just do it. Try to do something useful, but if you're just doing it for status or to prove that you can, those are perfectly good reasons to do something. I think if you're 18 or 22, the most important thing should just be you want to prove that you can do something. That should be that's what should matter to you. Just prove that you can. Prove to yourself, prove to the world. That's sort of number one. Don't let anyone tell you I'm not saying be bad person. Don't go start a hedge fund or something like that, But yeah, you don't have to be an angel. Just get out and do stuff. And don't give up, because life is super hard. It's really hard. It's really, really hard. It's not any easier now than it was in 1924, 1824. The only difference is today we're on offense and not defense, right? In 1824, people, is it 2024? I don't know what year it is, but anyway, the 1800s, people were just trying to survive. Now we're trying to push the boundaries. It's just as hard, right? It's not any easier.
Right.
So there's no reason to expect anything to be easier to come easily. And I don't know, a lot of people are cynical about the future and think America's not the land of opportunity anymore and all that stuff. It's not true. You just have to fight. You always had to. It was the land of opportunity in the 1800s. You had to fight tooth and nail then too. So, don't give up. Just keep trying. Have some chops. And just take failure in stride. Fall, get up, fall again, get up, fall again, get up. Don't hold grudges. People are going to be mean to you. They're going to hurt you. And people get better. Someday they'll be better people. And just move on, I don't know. Is that good enough?
Perfectly.
Yeah.
At the end of our show, we have a section called Overrated or Underrated, where we give you a topic or a statement, and you tell us what you think. Sounds good?
You're going to give me the topic?
Yes.
Okay.
The first one, Tony Leggett, sort of related to your work, overrated or underrated?
I mean, Tony's the most rated person ever. He won the Nobel Prize. Properly rated.
I saw him on the bus today morning.
You did?
Yeah, he was going to Loomis. I mean, his research center.
I'm a huge fan of Tony Leggett. Can I talk about Tony for a second?
Yeah, of course.
He is the incredibly classy, pleasant English gentleman. But he is an intellectual savage. And he loves a fight, and he is a complete rebel. Tony Leggett has more uncited papers than anyone I know. If you open up his CV, he has these papers with thousands and thousands of citations of Caldera and Leggett on dissipation and tunneling and all these things. But look at the end, hundreds of papers, 0, 0, 0, 0, no citations at all, because he's a absolute cowboy of a scientist, and he's the most intellectually adventuresome physicist I've ever worked with. So I'm a huge fan of Tony. I'd give him another Nobel Prize. He's just a great guy too. So big fan. So I don't know if that's under or over.
Yeah, when he came to talk to us, like one thing that he said was kind of like out there. He said like the future affects the present, and he didn't want to say more because I think he probably is working on some paper or something. But who knows?
I only understand 10% of what he says.
All right, next one.
I have 100% confidence in him. Yeah. Is there another one?
Yeah. Next one. The flux capacitor.
Isn't that from that TV show?
From Back to the Future.
I don't know what it is.
So
I don't know what it is.
I thought it was from your time, but I'll explain it to you.
I know you don't have to. I grew up in the 80s. I hate the movie.
Really?
I hate that movie.
Okay. So okay.
Freaking hate it.
We'll change
I hate the flux capacitor. Can I rant about that?
Sure,
too?
sure.
Yeah.
I hate Back to the Future for several reasons.
Okay.
It's a very entertaining movie, so I don't deny that. But the whole time loop thing is nonsense. Right, where you can go to some point on a timeline and then affect a timeline chronologically.
Right.
It doesn't make any sense.
Mm-hmm.
I hope I don't have to explain that because I don't think I have the energy.
You think it? Let's say.
But the idea that I can go back in time and then
Right.
change who I am and then come back, it doesn't make any sense
Right,
because
right.
that's not how I am.
Mm-hmm.
Because if I went back and talked to myself in high school, then I would have met myself when I was in high school. So I can't change me because I would have. You see my point?
Yeah.
So I hate the movie for that reason, but I hate it more for a bigger reason, which is that it creates, and many movies do this, especially Avenger movies. I hate the Iron Man films,
Oh my
especially. They create the misperception that great things are done by a person working by themselves in a building.
Mm-hmm.
And this Doc guy with the hair, he builds this time machine by himself in his garage.
Right.
And that is not how innovation happens. Big things are done by teams of tens to hundreds of people working on things over years and years and years. And you go into a big team and you work on a little thing and you never get to work on the whole thing. You work on a little piece. And it's a problem because kids come into graduate school and they have seen Tony Stark and they're like, I'm going to be Tony Stark. And then they get in, you've got to untrain them that that's not the way science happens, right? They're going to have to work as part of a team of people, especially if they're doing experiments, building a thing. So I don't know, I'm always fighting against this, I won't say the adjective movie, for the, and the whole lot of them, for the misperception of the way science happens that infects young people. So
I was actually reading about this in a book that I'm reading, and they mention like the invention of the light bulb, for example, or the telegraph,
Thomas
right?
Edison.
Right. So all these inventions, it wasn't just one person who made it.
It was not.
Right.
Thomas Edison had a big company of people.
Right.
Yeah.
And even
He
before,
was exceptional at getting credit for stuff, wasn't he?
right.
Yeah.
And even before the light bulb that he made got commercialized or like famous, there was someone else who had already dabbled in that topic, but never went successful, right?
Yeah.
So why is it that we idolize or associate just one person with so many inventions?
It
right?
is a failing in Western culture.
But it's also because we want to see ourselves in those shoes,
Yeah, I think so. Yeah, probably. Right.
which is a really interesting
But I
take
think that's a failing in Western culture. We sort of idolize the exceptional people.
Right. But it was never one person, which is something that we all need
It's
to
never
realize.
one person, right?
So you say it's a failure? Like,
I think it's a failing of Western culture that we do this.
but don't we want to, to be, exceptional to an extent? Perhaps the idolization is
Yes,
bad, but
sure. But what exceptional mean? What does exceptional mean? Right? Well, first of all, everybody's made out of the same material, and we aren't that much smarter than each other, right? Right? My head isn't 100 times bigger than yours. I'm probably not any smarter than any of the three of you or anyone watching this, right? So what does exceptional mean? Exceptional. The only way to be exceptional is to do things that are just. The only way to be exceptional is be persistent. I mean, I've done a lot in my career. The only thing I did differently than most people is I just didn't give up. Just kept going. I didn't let failure get me down. I kept trying. As my papers got rejected, and I had a lot of other hardship than that, I just didn't give up. That's the only exceptional thing I ever did. It's patience. So, but I'm not a zillion times smarter than somebody, or I can't go. They run the Boston Marathon. I think it's going on next week, or really. The difference between the first place, the greatest of all time, Eliud Kipchoge, and the second place person is tiny, tiny margins. We're not that different from each other. So I think it creates a false perception of what it is to be exceptional. I think we should try to be exceptional, but you can't be inhumanly exceptional. It doesn't. I think the Disneyfication of culture really bothers me because it sort of creates the perception that there's some people who can just fly or teleport through walls or whatever, and it's not true. Anybody who looks incredible, they somehow are in the right circumstances and made some good strategic decisions and probably had some luck too. Luck is really important. Yeah, so I don't like Disney either. I watch all the shows, so I'm not saying I don't watch them. I do, but yeah, I go to work and it irritates me.
do you have one?
Was there another one?
Something underrated or overrated? UIUC talk show.
I've never seen it.
No.
I've never seen it.
So earlier today, I was talking to another, good professor in computer science, a really good friend of mine, and she's quite special, and she's also gotten offers from these fancy, places. So those fancy institutions,
Yeah.
overrated or underrated, and why you decided to stay here.
Underrated.
What is this or
Fancy institutions,
Got it.
underrated. Well, you name one. I have friends at every one of those institutions, so I'm not going to knock any of them. Underrated. I mean, what did I say? Underrated or overrated? Fancy institutions are overrated. We're underrated.
First, why they're overrated, those fancy places, and why you stay here. Because you easily could have gone there, and whatever.
Yeah. I'm not going to knock anybody who decides to go work at Harvard or Stanford. I have friends who did that, and they're great people. So I'm not criticizing anyone, but there are burdens working in places like that. One of them is the cost of business is extremely high. So here I can get an NSF grant, hire 2 grad students, and go do some research with it. An NSF grant, I don't think it even gets you a grad student at Harvard or Stanford anymore. They have access to other sources of funding, and I have a postdoc who works at Harvard now. He seems very happy. So, but I think being at Illinois, the cost of business is just lower enough that you have more flexibility to take risks. That's my opinion. I'm sure people will disagree with me, but I think also that it's another thing that I like about working here is Illinois. We do absolute top scholarship, but I don't think it comes with the same pressures to be at the absolute top of your field. I mean, there's quite a few people here who are just doing okay, they're just doing their thing, and they're not in the National Academy of Sciences, but they're doing decent work, and they're in the middle of their field. And that you can just do that here. It's fine. It's fine. Have one grant and a couple of students and do your thing and publish. At Illinois, it's fine to do that. If you want to be a monster and take over the world, that's fine too. It's sort of it's open to different models, and I think that's really important. Because some of those people who are chugging along that don't look like they're top of their field, sometimes they're doing things that are extremely important that Thomas Edison's going to take credit for at some point. But he won't be able to do that if they're not there doing it, So, yeah, I feel like there's more ways to work here. There's more flexibility. And there aren't the expectations that you're king of the hill all the time, which gives you a license to take risks. Because often you try something risky and it fails. Usually it fails. And then you have a problem, right? Now you're not publishing and you lose some money, and here you're still a respected member of the community when you do that. So I think the lack of ferocious competition is better for science. But there's people at Stanford who are doing amazing, so more power to them. But yeah, I think it's just more about the right place for you.
And the last one,
There's another one. Okay.
1984, and
Book?
the idea of a dystopian future.
Do I think there's going to be a dystopian future? Is that what you're asking?
Right, and like the book, like how it portrays and.
Well, the dystopian future in that book was there would be a communist takeover and absolute fascist rule of America, and democracy would disappear. Are you asking if I think that's going to happen, or if I just think there's going to be a dystopian future?
Right.
You're going to think I'm stupid, but I don't. I really don't think there is. There's going to be war and some famine and stuff, and the climate is going to change, and humans are going to adapt and improve, and we're going to fix it. And I don't think democracy is going to die. And people are cynical about it because life is hard despite democracy. It always has been, it will always be. So people get cynical, but, you know, to quote Winston Churchill, it's the worst form of government except for all the other forms of government. No one's found a better system yet. And in the long run, I think, yeah, I'm optimistic. I think things are going to be okay. We're going to straighten out. The U.S. and China will iron out their differences. And there will be tension, but there will not be a war. You're gonna put this all over. If they invade Taiwan, you're gonna put this. I think they'll find a peaceful way through, and I think we will figure out how to manage the environment. Some species will go extinct, and everybody's gonna have to move out of Florida, and probably Arizona too. But we'll straighten things out and things will be okay. And we'll learn how to adapt and things will be better. And I drove my EV here to prove it.
You're saving the environment with that one. Like,
Yeah, I don't even know if that's true because now I'm seeing that the environmental impact of mining for all the lithium
That is
is a
true.
bigger impact than...
Buying, yeah.
But I'm viewing it as an R&D project and learning how to use other modes of transportation that are sustainable, even if that one wasn't helping at all. I don't know, I just think it's a cool car. Maybe that's all.
Well, and with that, we thank you so much
I gotta go.
for coming. And
It's been a pleasure. I've never had 3 people attentively listen to me rant about pointless things in my life, so it's been a true pleasure.
we didn't talk about the science and you know this sort of like new states of matter and all, like everything you've done in that field. So you'll have to come back in the future and
Sure.
talk about that. But
Yeah,
Thank you.
yeah, good.
And I think I like the optimistic perspective that you just happened to take in this conversation. Like I think you were surprised too that what the things that you were saying were that optimistic. And I think that's how our generation should at least look at the future if we actually want to change things. And like one of the things which you said was that to accept things for the way they are. But I think for this case, you almost got to work in that idealistic perspective or that optimistic viewpoint if you actually want to get to that change.
Yeah, and I don't want to drag it out, but I said treat the world the way it is, not the way you think it should be.
Right.
It doesn't mean accept it the way it is.
That is true.
Right? But you should be realistic about how it actually is. If you want to change it, you need to be realistic about the way it actually is and not think, well, it's really some other way. So, okay. We done?
Yes.
Okay,
Thank
good.
you.
Thanks, guys. It was very interesting.